Hi, I'm Nolan Kablishki,
And I'm Jordan Sawchuk.
and today we'll be talking about a very famous experiment performed in 1963 by Max Frisch and David Smith, which sought to measure relativistic time dilation by observing cosmic ray generated muons.
We're going to start off with a little bit of theoretical background on special relativity and time dilation, and we'll talk a little bit about cosmic rays and muons and try to motivate the experimental design a little bit.
After that, we'll dig into the experiment itself, which was based on an earlier experiment by Rossi and Hall. And the apparatus is elegantly simple. So we'll look into that, and then we'll conclude by discussing the results.
The theory of special relativity proposed by Albert Einstein in 1905 arose out of the need to resolve an incompatibility between Newtonian mechanics and Maxwell's equations. It comprises two postulates which are not on the surface overly complicated or surprising. The first states the laws of physics are the same in all inertial reference frames. This is an extension of Galilean relativity which applied only to the laws of mechanics. Essentially, one inertial reference frame is as descriptive as any other, and there is no universal coordinate system. The second states that the speed of light in a vacuum is about 300 million meters per second, independent of the motion of the source. The independence of wave speed and source speed is a property possessed by all physical waves, including sound, and forms the basis of the Doppler effect, in which waves become bunched up, i.e. more frequent in front of a moving wave source. One strange implication of special relativity is the phenomenon of time dilation, which in simplistic terms states that the moving clocks run slowly. It's described by this equation, which is worth investigating a little bit. First, we'll define the Lorentz factor gamma, which will simplify our equation. Note that since v is always less than c, gamma is always greater than or equal to 1. Moreover, since v is squared in the expression, the direction of motion doesn't matter. At 11,000 meters per second, the maximum speed reached by the astronauts of Apollo 10 during atmospheric re-entry, gamma is still basically 1. It's not until we start getting close to the speed of light that the Lorentz factor becomes appreciable. So how do we actually read this? Let's imagine a spaceship flying past a planet at constant velocity. At the exact moment the ship passes the planet, suppose that clocks in both reference frames are synchronized, and that observers in each reference frame have agreed to time some event which occurs aboard the spaceship. The first postulate of relativity allows us to think of the ship as stationary and the planet moving. Circles are a lot easier to draw than the Starship Enterprise, so let's think of it that way. When both observers hit their stopwatches, something's happened. The clocks are no longer synchronized. The time t measured aboard the spaceship, called the proper time, since the event being timed was stationary in the ship's reference frame, is less than the time t prime measured on the planet. Thus, an observer on the planet would conclude that the clocks aboard the ship were running slowly. Of course, it's not just clocks moving more slowly, but time itself. But how can this be? The flow of time feels constant to us. Moreover, time dilation is reciprocal. Observers moving relative to one another will see each other's clocks running slowly. And this feels paradoxical. How can one clock be both slower and faster than another clock? The physicist Steve Adams uses a geometric analogy to try to help us get more comfortable with this idea. Two people looking at each other from afar will simultaneously judge the other to be smaller than themselves. But perspective isn't mysterious, and things get even weirder if we allow acceleration, leading to the twin paradox, for instance. It's a small reassurance that the Lorentz factor is very small at slow or non-relativistic speeds, explaining why we don't typically witness time dilation, but these are big claims, so how can we actually demonstrate their legitimacy? If we could measure time dilation, we could obtain experimental evidence of special relativity itself. This is where cosmic ray-generated muons come in. Cosmic rays are comprised primarily of protons and alpha particles which travel through space at nearly the speed of light. Collisions between cosmic rays and the nuclei of air molecules occur frequently in the upper atmosphere, causing a shower of secondary particles. Among these secondary particles are negatively charged pions, which are highly unstable and decay in about 20 nanoseconds into a muon and a muon antineutrino. There's a lot of energy involved, so these muons tend to have velocities of around 99.5% the speed of light. Like electrons, muons are leptons, meaning they're not composed of quarks and they do not interact via the strong nuclear force. Their rest mass is about 200 times that of an electron, and they're very unstable, quickly decaying into an electron, a muon neutrino, and an electron antineutrino. Muon decay has been shown to follow an exponential distribution with a mean lifetime tau of about 2.2 microseconds. Exponential distributions have a property called memorylessness. If we zoom in on a part of the graph and redefine the axes, the function looks the same, and tau is still 2.2 microseconds. This will be helpful to us. Because the basic idea is this. We count the number of muons with a given range of speeds arriving at some altitude. Since the mean life tau is independent of how much time has already passed, it doesn't really matter what altitude. Then we go down to sea level and count the number of muons in a slightly slower range of speeds, accounting for deceleration by the slice of atmosphere between sea level and our previous altitude. If we apply our formula for exponential decay and solve for t, we are essentially reading the muons as a clock. In terms of our time dilation formula, this is our proper time. Then, dividing the altitude difference by some average velocity amounts to reading our terrestrial clock. By comparing these times, we can experimentally determine the Lorentz factor, thereby measuring time dilation.
Frisch and Smith had this exact idea in 1963. They were located at MIT, and just 2.5 hours away was Mount Washington, which is about 6,000 feet above sea level. Now, they had the altitude difference to conduct this experiment. They constructed a muon detector and used it at sea level and on top of Mount Washington. Then they counted the number of muons at both elevations. By comparing the two counts, they figured out how many muons decayed and if the muons were affected by time dilation. Here is the muon detector that Frisch and Smith used. First, I'll talk about the iron blocks. The muons enter the iron blocks at high velocity and collide with the iron atoms. When they collide, they are repulsed off the electrons by the electromagnetic force. This transfers energy from the muon to the electron. As a consequence, the muons slow down. The iron is used as a filter for the muon speeds. Muons going at 99.5% the speed of light will slow down just enough that they will stop in the muon detector and decay. Muons going faster will pass right through, and muons going slower will not have enough energy to get through the iron. Since muons also collide with air molecules, this has to be taken into account for the differing altitudes. For this reason, placing an equivalent amount of iron on both detectors will not work. This is because the muons have to go through an additional 6,000 feet of air before reaching the second detector, so they'll be too slow to pass through the iron. Therefore, a few layers of iron are removed that is equivalent to slowing down in the air. So now the muons in the speed range can pass through and decay in the detector. Next up is the scintillator. The scintillator is the most important part of the muon detector. It is made of plastic, mainly carbon atoms, and when muons come in at high velocity, it will collide with these atoms and excite their electrons. The electrons will then relax and release a photon. The muon loses energy as it does this, and so the muons in the certain speed range will slow down to a rest. After a short amount of time, it will decay and release an electron. This electron will collide with other atoms, which, by the same process, will produce photons. These photons are picked up by the photomultiplier, which, by the photoelectric effect, produce a current that can be read by the oscilloscope. Now with the oscilloscope readings, they only want to count the muons that decayed in the scintillator. So they removed all spikes from the initial collision, and they only kept the spikes from the decay. Now they took a long exposure of the oscilloscope, and all they had to do was count the lines to determine the number of muons that decayed in the scintillator. So what did they find? Well, on Mount Washington, they observed 563 muons. And you'd expect most of them to decay before they reach the ground. So classically, you would expect about 27 muons to be observed at sea level. That's totally not the case. They observed 408. Looking at our exponential decay curve, we can see that by observing 408 muons, they experienced about 0.7 microseconds. Classically, they should have experienced about 6.4 microseconds. Now for the big question, does this prove special relativity? Well, recall that the time dilation is given by gamma, the Lorentz factor. We can solve for gamma by taking the time they should have experienced classically and dividing it by the time they did experience. And this shows that the muons experienced time 9 times slower than a stationary observer. Plugging their speeds into the Lorentz factor shows that they were expected to experience a time dilation of about 10. So these results are extremely close. Doing some deeper analysis, accounting for all the errors that Frisch and Smith made, they measured gamma to be 8.4, and they expected it to be about 8.8. So this is strong proof for special relativity.
The observed Lorentz factor of 9 may seem quite a bit different than the theoretical value of 10, but keep in mind how steep the function is. This is really just a matter of a velocity of 99.4% the speed of light versus 99.5% of the speed of light. So given the minimalism of the apparatus, it's a pretty good result.
Frisch and Smith also conducted further analysis that took into account the errors in the experiment. For example, they had one too many layers of iron on top of the scintillator. As well, they assumed all the muons entered incident to the detector, and this is obviously an oversimplification.
Far more accurate experiments have been performed. Notably in 2014, scientists in Darmstadt, Germany, measured the time dilation factor gamma with an uncertainty of about 2.4 times 10 to the negative 9. Nonetheless, this experiment by Frisch and Smith really stands out for its ingenuity.
And they also made an awesome video to go with the experiment, and I will link that in the bibliography if anyone's interested.
Should definitely check it out.
Thank you very much. Goodbye.
Thank you.